Yeah, hello. My name is Jan, and this talk is going to be about the geometry of in-context learning. What this project, which I started out with Jan-Hendrik Kirchner, ended up being about, let's say, and we worked on this during my PIBBSS fellowship in the last 3 months. And I'm going to give you the TLDR straight away. We think that you can phrase in-context learning in some cases as some sort of sequence extrapolation on a geometry that has been shaped during in-weight learning. And we're going to dive into what we mean by that throughout this talk. Great. So here's an overview, and I thought it might make sense to sort of go through the talk in the way we went through the project and kind of the steps that we took and the decisions that we made along this way. And this is what this overview is about. I went into the fellowship with this question, which is written here, namely, what is the neural basis of learning? This is like a very broad question, but in particular in context learning, which was a phenomenon that I had encountered, let's say, anecdotally at some points throughout my PhD. But yeah, I sort of was curious to see whether one can make some more progress there. And the steps through which we went was, why is it interesting to study in context learning to begin with? And then become clear about, okay, what maybe defines in context learning and how is it different to something which is typically contrasted to it, namely in weight learning, which I'm going to abbreviate as IWL. And then we were thinking about, okay, now we sort of know what it's about, but what is maybe the right frame to do some more analysis on it. Then we built a hypothesis in this frame, and then we went on to test that, both in a toy setting and in a real setting. And these will be the stages throughout this talk that I keep coming back to. All right, so first question was, why study in context learning, or really like learning in general? And I have a background in neuroscience, so I was aware that there are like these, let's call them operational, you might also call them like physiological differences. For example, in BNNs, that is biological neural networks, or the brain, there's long-term synaptic plasticity, which kicks in, for example, if you're learning a new language, then you sort of tweak your synaptic connectivities, not very much in a conscious manner, over the course of weeks or months, and in the end have a differently configured connector. This is in contrast to short-term memory, where, let's say, I can teach you the rules of a board game in, I don't know, 10 or 20 minutes, and you will be able to leverage that from short. And this you might maybe call a form from in-context learning, which is less persistent and works on a much shorter time scale. Now, there's a parallel to this in artificial neural networks. Let's say maybe the more traditional view is that information is burned into weights during a training stage, and then later during testing, this information is being leveraged. However, more recently, there's also the stream of in-context learning, where you can supply information in a prompt instead of changing the weights, in fact, without changing the weights, and then leverage that. And this really culminated in, I think, a recent paper, I think it's this year from Google, where they put in a dictionary of a new language. It's called Kalamang. And then within the same prompt, they put a query to translate an English sentence to that language. So you have this insanely huge context prompt, and then are able to leverage it in order to arrive at a translation of this English sentence into Kalamang. And this worked essentially at human performance, which would have needed to leverage these synaptic changes. Now, I don't think at all there's like a one-to-one correspondence, but maybe this shows that there is like this operational difference, both in BNNs and ANNs. Now, from a safety perspective, we might ask, okay, there seems to be this new, very powerful paradigm, which seems to be able to do a lot of stuff, which we believed previously to be only possible by changing your synapses, is there maybe a functional difference at all based on some principled reason? But really, one can also ask the more general question, which we were not hoping to answer because that would be unrealistic, but try to work towards a model theory of framing for in-context learning, which then one could build off collectively to talk about learning. All right, so this was the motivation. But what is learning actually? So I don't really have a good answer to that, and turns out to be a very surprisingly hard question to formally define. But like one take could be that it's just inference from finite data, which maybe some people might call glorified function fitting. That is, okay, in some manner, I give you some set of pairs, of input-output pairs. So these would be these exemplar points in this very simple 1D function example. And then I give you a test point, and I ask you to do a continuation of the sequence. And what you would do is you would maybe have some model about how these data points, how these labels have originated from the data points in the training data you saw, and then form some sort of Bayesian posterior about it, which however hinges on the model that you put in, inductive bias, which could either be shaped by your architecture or also during your learning procedure, which you would then leverage to arrive at a prediction. So that's maybe what learning reduces to if you try to be very minimalistic. But how about in-context learning and in-weight learning in particular? They're like both kinds of learning, but how do they differ? And the first thing to note is that they are very similar in a sense on the function level in the following way. So here's in-weight learning on the left. And what you do there is you have a set of exemplars as what I showed you just before, but now like the training data points are like entire sequences that you have in your training set. Then you change your weights. And if I now give you something to predict from, say, this sequence, then you would be able to leverage the structural knowledge that you've acquired during in-weight learning and make a prediction from that. In context learning, very similar thing happens, but the location of the train set is somewhere else. It's namely put just into context. And then without any weight change, you generalize from that. So in that sense, these paradigms are very similar. But operationally, they are different. And this is important because one might think, okay, so apparently you can do all things in context, so why bother changing the weights to begin with? But like empirically, at least, this seems to be like a more powerful notion. And one very simplistic reason why that is what we try to give in this very simple sketch. So consider you have a two-layer neural network, like for example, this sketch here, which is already reminiscent of a transformer. It's just like an input, and then you have two matrix multiplications on top of it. And this grouped layer one, you might call phi. And phi is what I will use to denote an abstraction in what is to follow. Then you can decompose the change in the output, essentially by the product rule, into two terms. One is controlled by a change in the weights, and the other is controlled by the change in activity. Now, change in the weights is what we already know from in-weight learning. You change your synaptic connectivity, and this will induce a change in your output. Change in activity is where in-context learning comes in, because if I supply something different in context here in these input sites, this potentially will change my hidden layer activations and gate entirely different subnetworks of my big architecture, which will then also induce a different output. So this is how both terms can induce an output change. But there's like one thing which potentially explains why in-weight learning is more expressive or more powerful. That is because by changing your weights, you have more parameters at hand. Let's say n denotes the dimensionality of your hidden states. Then, because the weights are all-to-all connections, you have n squared parameters. However, by changing your activations, you are more confined. You have something like order n parameters, and that's how you get more expressivity out of the in-weight learning paradigm. yeah. All right. So this is how in-context learning and in-weight learning are functionally similar, but implementationally, operationally slightly different. Okay, so now I want to take a step back and after defining what is in-context learning, zoom out a bit to try, yeah, like one goal is to try establishing a frame in which to talk about in-context learning, but really also to recapitulate the process that Jan and I had with our joint background being in computational neuroscience. And this was acknowledging what I would say is like a convergent evolution between the fields. And this will be like a slight excursus into history, let's say, but maybe it's interesting. So in the early days of neuroscience, sorry, this should of course say 1919 here, Ramón y Cajal, who was like a Spanish neuroscientist, did studies on single neurons in frogs. And this literally went by inserting an electrode into a cell body and measured the currents that come out of it. Similarly, Hubel and Wiesel several years later looked at neurons in the visual cortex of cats and found that they are responsive if you present them with a given directionality of a visual bar. So you have like a horizontal line on some screen or something. Then they will only respond if it's horizontal, but not if it's vertical. And this has been called sometimes the single neuron doctrine, that a single neuron corresponds to a given feature, like this orientation of the bar. Similarly, for RNNs, for example, here this work by Go and Ola found that there are neurons which are responsive to some features. For example, here this happiness neuron or the sleepy neuron, which really looks quite sleepy. Then a next step in this development was what I would call broadly the linear representation hypothesis. Also, sometimes it's called population coding in neuroscience. And like a seminal paper there was by Georgopoulos, who found that, okay, it's not necessarily true that a single neuron will correspond to a single feature, but it can be more subtle than that. For example, here again, you have some directional input. So imagine these directions are orientations of a bar. And then associated with it, you have the responsiveness of a neuron, here indicated as a firing rate, or spikes emitted by second. Then you will find that this neuron has like a preferred direction, namely here this bottom left, but it's more gradual if you degrade from this direction. Namely, you still get a response when the direction is somewhat shifted from that. And this means that there's like more something of a distributed representation, which means that maybe any given feature is associated with the direction in neural space and not so much a single axis aligned direction as the single neuron doctrine maybe would say. And very similar ideas have been recapitulated in this paper by Nelson L. Hage and Chris Ola very recently by Anthropic, I think, where they wrote this up in a really nice fashion. But this has really been an idea which has been around in machine learning for much longer. And then there's a last step, or let's say most recent step in this evolution, where one has said, well, instead of looking how a given input corresponds to a given feature, why not take many inputs at the same time, feed them through a neural network, and then look how they interrelate? And this gave rise to the notion of neural manifold geometry, which really tries to capture the dependencies in between responses to different inputs, which you might want to capture in this representational similarity matrix here, where you try to look what is the overlap between any pair of inputs. And people have found very interesting things, namely that neural activation space often captures some sort of geometry, which is somehow semantically reminiscent of what you see in the real world. For example, these latent activations here had been associated with a circular reach to grasp task, or this torus here had been motivated from some normative theory about navigation in, I think, rodents. And very similarly, again, this geometric perspective has very recently found a lot of interest in artificial neural networks as well, where here the days of the week, for example, lie on a semantically structured manifold, or here this belief state geometry by Adam Schei. So there's this, I would say, almost striking convergence, and to some extent, sadly, independent convergence of interpretability in brains and in neural artificial networks from a very local to a very global integrated perspective. And Jan and I think that this is very much a natural evolution, which will capture more information. And by leveraging synergies between these disciplines, there's potentially a lot to be learned. Okay, so now back to in-context learning. Why is in-weight learning, or why is geometry, and as we will see now in-weight learning geometry, particularly useful? And before we move back to sequence prediction, let's get inspiration from a classic ML task, which is the XOR problem. So here's the XOR problem. You have a 2D space, and I ask you, if presented some vector in this space, to respond with class blue, if it's here or here, and to respond with class orange, if it's here or here. So this seems fairly easy. It actually is fairly easy, but for a machine, it's not that easy, at least some years back, because similarity in this space does not imply semantic similarity. For example, you can be very close here, and similarity I measure by the dot product. You can be very close here, but your label is different. So what you can use a neural network for is to lift this entanglement in input space, which happens by this feature map. And this will define a feature space where this input manifold has been entangled. And this I would call linear geometry, because it's like a set of mapped input features, as we just discussed. And here it holds now true that similar embeddings will entail similar labels. And from there on, it's very easy. You just take like some hyperplane and you're able to pull off this classification. And you can also formalize this. This will be useful in the next slide when we talk about sequence models, by writing the output that is produced by that with help of something that is called the kernel trick, which I won't dive into, as a similarity weighted sum, where now crucially these weights that weight the train labels are measured in semantic similarity as opposed to input similarity, where this wouldn't work. All right, can we somehow use this for sequence models, which is what we're interested in order to understand in context learning? So here's the story in this classic machine learning paradigm. We have some training set and then we have some testing set. And here we have this algorithm as per the kernel trick, which allows us to arrive our predictions by a similarity weighted sum of inputs. And the geometric picture to have in mind there is that you aggregate nearby inputs in the semantic space according to their distance, and you disincentivize far inputs. Now, how does this look like in sequence models? In sequence models, and this is now my very toyish sketch of the imaginary one-layer transformer, you have a sequence of inputs. You map them into some embed space as well with a causal attention mechanism. And then from that, you craft your output prediction. And if you write down the attention operation that happens during this as the softmax operation, where keys and queries that depend on the concatenated collective input up to there, you get this formula here. And if you squint really hardly, and this is, for example, what has been done in papers like the one by Kataropoulos or in this blog post by Bhaktra, this looks very similarly to this formula here in the classic machine learning task. But does this have some geometric correspondence here? And this was what gave rise to some hypotheses that Jan and I had developed. And the poorest take that you could have of it is that chain of thoughts are chains, with a chain of thought being what is Lerich doing in context learning. A bit more detail, it means that in context learning in transformers leverages some sort of geometric chain of latent states. And this is illustrated down here. So you have again this transformer architecture, which is a sequence of hidden states. And the hope is now that these hidden states are configured in a semantically meaningful manner, as we saw in these neuroscience and mechanistic interpretability pictures before. So that's the hypothesis, but we didn't know whether it's true. So we went on to test that, first in toy tasks. So here's the toy task. And I put here some dimensions for the people who are familiar with it. Maybe it helps. So what was the idea with this toy task? What we wanted to do is what I showed in the earlier slides, namely time series forecasting in the simplest example that you could think of, which is 1D time series. And to this end, we construct these sine waves and then asked or like trained the architecture to forecast the next token. So this is like a set of input sequences which we train on, and this was the set of labels that we trained on. Now, maybe you encountered in high school that sines and cosines, trigonometric functions, are actually defined by projections from a circle. And our hope was that by using such a task, we might be able to rediscover or have the architecture implicitly learn this geometry, which is actually in some sense the ground truth that generated these data. And what I mean by ground truth is that it's in the sense the simplest algorithm that you could leverage to generate a sequence of sine waves. So this is here illustrated in a bit more detail, that you have these points on a manifold and then, on the circular, on the circle. And then you project them onto some plane. And these projections here, they will be what gives rise to the 1D sequence that we train on. And to do this, we again take our transformer architecture. It has some number of positions. It has an input dimension, which is 1, output dimension, which is 1. So this is different from, for example, the natural language modeling setting, where this would be a high dimensional vocabulary size dimension. And then we give it like a latent dimension, which could also be larger than 2. And we actually made it larger than 2, but it should be at least 2. Okay, and then there is some batch, but this is irrelevant for this setting. Okay. So how does this look like? After fiddling around a bit, what you get is something like this. So on the x-axis here, you have training time as indicated by these titles. I hope they're readable in percentage of the overall training. And on the y-axis is the layer, the depth in this transformer. So now it's not a 1-layer toy transformer anymore, but I think a 5-layer transformer here. And what you see is that, okay, first the transformer manages to do this prediction task as you train it. And it does so by developing latently something which at least resembles the circular geometry which we generated the ground truth for. Okay, so this was quite cool that it worked so well, because it actually enabled now the transformer to not just, like straight continue this function here, or maybe, take into account the curvature, but actually do the oscillation of a sine, which presumably it could only have done by developing this latent representation. But it was not quite clear whether this is some like correlational artifact or whether this is really used for prediction. So what we did is look at the attention scores during training. And what we see there is that this slight faint highlight, which is centered around the diagonal, is emerging. And what this means is that indeed such a weighted similarity prediction, as we were looking at earlier in this formula, is happening. So it seems to attend to tokens which are close by, and close by tokens here mean tokens that are close on the chain. So it seems to actually use the geometry that it has learned and extrapolate on it in some leaky integrator manner in order to arrive at the next position. Yeah, so this is what we did in this toy model. So here's the summary. So latent manifold structure is discovered during training, and it's also what is leveraged for prediction. So that's the toy task. And we were very encouraged by that and very excited. So we went on to look at or to search for really chain-like geometry in real tasks. Now, this turned out to be much harder. First problem was that this notion of PCA, which I used to just decode the circle from the simple task, didn't work anymore. So we needed some heavier tools for that. And we borrowed tools from topology. And I'm really not an expert, and there's like beautiful mathematical theory behind it, but I'm trying to give you my understanding of it, how this works. So suppose I have some sequence of latent states of which I don't know whether they are in a chain-like typology, and I would like to test for that. For example, this sequence here. So what this topological approach does is it takes each point and it draws a ball around it of a given radius. And then it increases these points in size consecutively. And it tracks or logs this on this sort of topological barcode. Now, what happens if you increase these circles and indeed a chain is present is that you get this signature here of a bar popping up. This first bar just being a baseline, which is kind of like always present. And the second bar means that there's like a pairwise connection between points, like a pairwise intersection of these balls that you draw around it in the latent space. Then you continue to increase these balls. And what then happens at some point is that these spheres start to intersect beyond the nearest neighbor. So here you can see the yellow sphere intersects with the blue spheres, for example. And this will then give rise to a final bar, sometimes called the death of this topological signature. And okay, so this would presumably be a good tool to test for such a chain-like geometry. But we first wanted to check whether, this holds up to some sort of smoke test. So what we did is construct a low-dimensional chain here, just a circle in 2D. And then we would feed it through some sort of distortion mechanism, which is parameterized by some parameter g here, which I will now vary. And then what is shown here is this barcode, like algorithmic implementation of this barcode, and just as a sanity check, some UMAP mapping, which actually under the hood does an almost identical thing to developing these barcodes. And then as a control, okay, we just take some random data, which wouldn't be a chain, so kind of like the null, then also do UMAP on that and show the barcode of that. And if I now play this movie, so here it goes, what you can see is that for the chain, you have this signature here, and as I increase the noise at some point, so you can see G varies, this distortion strength, at some point the signature disappears. And you can also see that the chain structure is destroyed now. And in contrast, on the bottom panel, the UMAP and the barcode of the control just don't show any signature at all. A brief comment here, which struck me as impressive, is that UMAP seems to capture this notion of chain, even then when the barcode already fails. And there's some interesting details to that. Happy to talk later about that if somebody is interested to the extent that I understand it. Okay, so this was a powerful tool at our hand to study chain topology in larger models. So, or larger models and real tasks in particular. So that's what we try to do. The first task that we looked at is a very recent one, which has been used on chain of thought or in context learning, namely this one by Brinkman et al. And what you do there is you train on a set of graphs, and a graph is a list of edges. And then you give the model this list of edges, in context and ask it to find the shortest path between an input node and a final node. So it's sort of like a path binning algorithm, but the graph configuration is very simple, so it's not so hard. And then again, we train a transformer on that. That's like a fairly straightforward task, so we can do actual training on that. And then we again plot training time against layers. And kind of these plots are super hard to read, but that's partially intentional because these analyses are so preliminary that I don't think anything precise should be inferred from them anyway at this point. But what you can see very coarsely, at least, is that in the beginning, there isn't any topological structure, and don't pay so much attention to the barcode, but rather to the UMAP, because I think this is what is more meaningful, or maybe I should say UMAP is some sort of fairly general dimensionality reduction mechanism. And what you can see curiously is that at some intermediate stage in training, you see something which has a lot of chain-like features. However, then as you train, and even across layers, however, if you then continue to train, this structure seems to disappear, which was very confusing to me, and I don't have a good explanation of why that is. It could be that chain-like topology actually is not useful then anymore, but you rather need some sort of more abstract structure, which you can't really decode from geometry. Okay, so this was this somewhat synthetic, but at least useful graph navigation task. Then we also wanted to train it, test it out on natural language processing, of course. And what we did there was consider this tiny stories data set, which is really cute. It looks something like this. And it's so simple. It's like children's stories that you can fairly quickly train on it. And here again, we have layers of our training time. And we see not much change structure, unfortunately, here at no stage in training. And I did some preliminary hyperparameter search, and I wasn't able to get it out. Neither was I able to get it out by going from per character tokenization to per word tokenization, where the idea was, okay, if you do per character tokenization, maybe you have more fine-grained control over the sequence of states because you don't have so many jumps between different tokens. But this doesn't work either. So in general, I'm very confused by what is going on here. Although maybe you can see some signatures in some of the plots, but I'm really not sure whether there's any chain to be found there. All right, so then lastly, I want to talk about something beyond global geometry, namely local geometry of chains. So whether or not we have some global geometry, as for example, would be accessible by these topological tools, we can ask, okay, what is the local structure of these chains? Presume we have some more or less intact chain. And what you could do there is measure something like the tangential angular change. So suppose I have this sequence of states here. I could measure, well, what is the angle between these vectors? And we did this on a fully trained gamma model. So this is now a converged model. And we tested that in a contrasting approach. So like we found that these angular changes are doing something completely wild, and it was very hard to see what they are doing at all. It seemed that there's like a 90-degree change from every position to every position. So in order to elicit any signal from that, we thought like, okay, maybe we need to do a contrastive approach. Maybe we need to just compare two things which are really, really similar, and maybe then we're going to see something. And that's what we did here in this task, where we put the same input prompt, despite for a slight perturbation, which was a semantic error, which was syntactically the same in both sequences, but there was like a semantic difference to it. And here is a very simple example where I have just the integers from 1 to 9, but then in the orange prompt, there's an error introduced. And what you can see is that, okay, up till there, due to the seed being equal, these latent changes, these latent chains, quote unquote, will have the same angular change, but then at the introduction of the perturbation, there will be a deviation. And then, okay, they do something from there on. So this was somehow interesting. Like maybe it was to be expected because the model of course then responds differently to it, but it seems to be encoded in this chain angles. All right, and then we wanted to push this a bit to the limit and introduce the harder task. And here the task now is these two prompts, again, syntactically similar, but there is like a subtle error. I'm not sure, maybe it is too small, so I'm gonna read it out. So it says, I have 5 apples and you take 3 apples from me. Afterwards, I have 5 minus 3 apples equals 2 apples or something, but this is omitted. But in the second sequence, I will introduce something which doesn't follow, which is sometimes called non sequitur, hence the name here. Namely, although I say take 3 apples here, in the formal subtraction, I subtract 2, which doesn't make sense, right? And okay, here I have this entire stack of gamma layers, which is of course way too small. So I put here the angular changes and ignore the black line here. Just means that the norm is more or less constant throughout the sequence, so that the sphere picture is roughly correct. And what you see here is that in early layers, these sequences lie on top of each other, and they continue to do so, and they continue to do so until at layer, let's say 35 or 37 or 40, you get this ever so slight deviation here. And then as you go to the output layer, where you again have to output words, there they more or less align again. So it seems that these more subtle changes only emerge at very low levels, very deep down in the model, which seems to be compatible with this notion that the deeper you go, the higher the level of abstraction and global understanding becomes. All right, so I hope from these plots being super coarse, it was already clear that this approach is very limited and also doesn't work much, but I think there are like other caveats to it, and I wanted to mention them here. So one is that embeddings in modern language models contain positional information. And now you might ask the question, well, then obviously we are just seeing the positional encoding here when we see these latent changes. I think there are 2 counter arguments to that, which at least make this somewhat sensible. One is that we only see this through our training, for example, in this graph prediction task. So it hasn't been there at initialization. That's part of the reason why we looked at this training to begin with. And then, even if there was no difference throughout training, no noticeable difference, I would still argue that it's somehow non-trivial that the model would represent a chain latently, even if it has positional information, because then the model apparently thinks it's useful to geometrically emphasize this chainness, the sequenceness, which we see because we did this UMAP, which is like an unsupervised mapping. It doesn't try to actively decode or regress something onto a chain. It's really just like generic UMAP, let's say default parameters, and you see this kind of like out of the box. So it seems to be very prominent in the model. But then like the much bigger caveat is that we try to make transformers stateful here, saying, okay, there's something like a vector state which captures somehow all of the semantic meaning, and then you just have to think about a sequence of states. And I think this picture is inherently flawed because the transformer always has the ability to look back at more distant tokens and being able to aggregate over that. So these are my 2 biggest concerns, I would say, but I'd be curious on your thoughts later on. Okay, so to conclude, the question which we set out into this project is, what makes the neural basis of learning, in particular in context learning? Because this seems to be like the strikingly, superficially, physiologically different paradigm from in-weight learning. And one thing to point out is that, okay, in context learning is kind of similar to in-weight learning, functionally speaking, because it just puts the trained data into context. And okay, then you have the same data and you can just do the same with it. However, operationally, there is some difference because changing the weights is like an order n squared parameter operation, whereas in context learning, you can only change the activations and do some gating within your already learned model. And we map this onto this geometric picture by saying, okay, learning the weights sort of establishes your state, your manifold geometry to work on. And then like in context learning, at least this was the hypothesis, would be able to leverage this learned geometry, right? Like think back to the XOR task where we needed in weight learning to disentangle the initially tangled input space and then work on from there. So these intuitions gave rise to this chain geometry hypothesis, which we then went on to test. First in toy tasks. Yeah, this worked very nicely and we were able to discover, recover the geometry that initially gave rise to the sequences. At least, you know, it looks like it a bit. And we also found that this is actually being leveraged from the model by these attention matrices, which have this exponential window decay along the diagonal. And then we went on to test this in real tasks, but we found that this is super hard to detect. I would not say with the current state of my knowledge that it is present. Even if you employ more powerful tools beyond this linear PCA by leveraging these topological tools. But you can try to look at more local structure with these semantic contrasting mechanisms and see some abrupt changes in the chains. Okay. And with that, I want to give some outlook, what I think would be interesting next steps to take the project to. The first obvious is, okay, like sometimes there seems to be maybe a change even in the natural language learning tasks. Now, is this change structure there or isn't it? Right now, it looks like it isn't, but maybe it's just a question of playing a bit more around with the parameters of the topological embeddings. A second question, which I would find interesting, is what happens if you intervene on the chain geometry? The chain geometry seems to be leveraged in prediction, at least in the toy task. So this potentially introduces a new modality to intervene on the model. Instead of steering a given activation vector, you could, similarly how there was this gradual history in neuroscience and machine learning, you could now intervene on the entire geometry of the manifold and think about making like a smooth manifold more curved or so and see what this introduces on the model output. And then lastly, and I think, yeah, more speculatively, there's something which you might call weak to strong supervision, which really picks up this idea of two chains being congruent or not being congruent. So let's say you have a model which you trust. Let's say you call this A, and you give it some problem on which you expect sensible, faithful reasoning. And you measure this according to model A. And then you have your new to be deployed model B, and you prompt it with the same task, and you see what kind of chain it has latently. Now, it might produce the same output, but maybe the chain by which it arrives is actually a different one. So by that means, you could assess faithfulness of model B as measured per congruency in neural space to model A. Yeah, but maybe like the most general, and I think what Jan and I are personally most excited about development that this project tried to jump onto, let's say, is this notion of neural geometry, which really seems to generalize existing paradigms. And there seemed to be this convergent evolution between neuroscience and artificial networks in using it in order to do more meaningful interpretability. So it seems like there's a lot of potential synergies there to be leveraged, which has already started to be acknowledged by people. But potentially there's much more to come. Yeah, so with that, I think I'm done. I would say a very big thank you to PIBBSS, which made this work possible over the last 3 months. I enjoyed it tremendously, and to all the kindness that I experienced from all the people within it, including the organizers, fellows, and people being around in the entire LISA space. I had a great time. Yeah, and with that, I would be happy to jump into any discussion.
Thank you so much, Jan. Clem should be joining us as an MC as well. But yeah, everyone, please feel free to raise your hand if you want to ask questions live, or type them into Q&A or into the chat. Welcome, Clem.
Hello, yeah, any questions from the chat? As always, I have...
Yeah, we do have people with hands up. Richard, then egg syntax.
With respect to checking the alignment of a chain A in a weak model to a chain B in a strong model, would there be like common bases even with which to orient those?
Yeah. A priori, I think not, right? You might expect, let's say, model B to be much more high dimension, for example, because it's a larger architecture. But the idea would be something like, let's say, natural abstractions, that you have some subspace where the manifold lives, which you can align to by a linear transformation. So let's say I have two planes, like this plane and this plane. They're both planes, and there's a linear mapping which will map one plane to the other. This is called like a progressive transformation. So what you could do is see whether there is such a linear progressive transformation that maps one sequence to the others, and that would at least give you some manner of facilitating this alignment.
Thank you.
Hey, terrific talk. Thank you very much. There was one section that I was a little confused about, which is when you showed the attention scores. Looking at those, right, it just suggested that what we saw was tokens attending to nearby tokens. And then you get this sort of interesting rectangular patterns along the left and bottom edges of your matrix of attention scores there. Can you say a little bit more about that? It wasn't clear to me how we could take this as evidence for the for anything. Really?
Yeah.
Sorry, that sounds terrible, but that's not what I mean. Just it wasn't.
Okay. So like first I want to say, like, this is definitely only evidence, if so at all, for the toy task. But for the toy task, I believe it is. First thing to say is that these rectangular things here, I have no idea what they are. I believe them to be artifacts and of some sort. And note that they only appear either early in training or in the, I would say, non-semantic tangled layer. So here I wouldn't attribute any meaning to them. So basically, I think you can safely forget about them. As then for these attention scores, what this means is first you have causal attention. That means like all the future is masked, being this dark blue here. And then, okay, like every token attends to itself. This is the diagonal here. But then with a slightly weaker score, it attends to the immediate past and less so to the more distant past. So this is what happens if you go here. So the easiest way to see this is to start by the last token in the sequence, which will attend to its predecessor, and then ever so slightly, or like more slightly, decay towards the more distant past. And in that sense, I would say, okay, let's say this token here, it attends to this token very strongly, and then this one, and then this one, and then this one, but not to the one here. And here in the manifold, that would mean these are the relevant tokens that it attends to, the ones that are close on the manifold. And then these actually enter into the prediction.
I see. So it's like it's noticing that locality is important, and that suggests something like a chain-like structure.
Yeah.
Okay, that makes sense. Thank you so much.
Welcome.
Nice. Yeah, I have my own question as well. Yeah, this is really great. One thing that I'm interested in and a bit confused about still is I think this point that you kind of made it a little bit at the end with this thing that like transformers aren't stateful, and this is like a drawback of this. And yeah, I'm like struggling to figure out how deep that problem goes. And in particular, I'm like looking at this like this slide actually in particular, exactly. And I'm like, well, each token can only attend to the tokens before it in like previous layers. You can't look at the same layer, previous token activation at the same layer. This is not information that any given layer has access to.
Yeah.
And so it's not clear to me how it's using this geometry, given that it like at a given point, it can't really extrapolate from the previous points because it doesn't have direct access to the previous points. It only has access to the predecessors. So how are you imagining that this extrapolation operation actually works?
Right. Yeah. Okay, so yeah, when I talk about this extrapolation, I'm thinking about the attention actually operating in the same layer, or like in some sense, I would define the states that are being attended to as living in the same layer effectively. Maybe they are located in the previous layer, but I would say, okay, it's actually doing the same thing. If you look at this here, okay, let's say you want to make your prediction at Y, then you take the similarity score, however, in one layer deeper down. So you measure similarity here, and this is then.
So if you look at the Y in the top left,
yeah,
it doesn't have access to the one which is to
this one.
No, but also the one diagonally down from that. So go down one, like it doesn't have access to that, right? There's no line from that to the final Y. So I don't see how it's ever using that information.
Okay, maybe it's like a question of definition here. Like, so
I think this is something like, by the way, this is something I'm just generally really confused about in these. I think sometimes the implementation is different. So sometimes the implementation is that actually it can attend to the previous layer in all context positions. So you just would have another line in your graph basically from phi to Y. But I'm just, this is something I'm not sure. If anyone in the chat knows any answers to this, I'm also very curious to hear, by the way.
Yeah, I would have to think about it more carefully, but like the way I think about it is, okay, so this operation is what's going on in any given layer of the transformer.
Yeah.
And then you can think of these sort of as, this as sort of your similarity metric, and these being the states being aggregated. And in that sense, it works in the same layer. And this then gives you the output for the next layer, so to say. But
right, yeah. Yeah, that suggests a slightly different architecture to the one drawn. Matthew, do you have an answer to this, or is it a different question? Have you been given access to speak? I'm not sure if I have the ability to do that. Boom, 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 boom. Okay. Yeah, maybe we'll go back to Matthew in a second. But yeah, so let's suppose that, I think this looks correct based on the equation as well. That this token here has able to look at all of the previous tokens. I'm curious what makes the like I get intuitively, I feel this thing that you're saying of like the next token being like some kind of like extrapolation of all of the things happening in the previous layer makes sense to me. But yeah, I'm wondering like what that operation actually is. Like why is it that your attention score has this like local shape if you're like doing this extrapolation from the previous tokens in this way? Like what's your, and like, especially if it's like a more complicated manifold than just a line, like what does it mean to like look at the previous n tokens and then extrapolate?
Yeah, why the last by the last tokens in particular, right? So I think for the toy task, I would say the answer is something like things semantically are expected to be smooth. If you talk natural language, you would expect, okay, there's some notion that, I have like a coherent, smooth chain of thought somehow. I don't make sudden breaks in my logic. And this was the intuition which said, okay, hopefully there's like some semantic space on which prediction actually means going forth smoothly. And what does it mean to go forth smoothly? It's like take your last endpoints and kind of draw a line. Like just continue this manifold with which whatever is the local curvature. And to estimate this curvature, you shouldn't care about points somewhere beneath here, but just like the brink of this manifold in some sense. So
And is that a linear operation always? Like, it seems like it probably is, but I'm just curious. Like,
you mean this
what are you?
extrapolation?
Yeah, on like a curved manifold.
Yeah, you can, for example, you can like, okay, if you want to estimate curvature, for example, to do like a very broad forecasting extrapolation of this manifold, you would need something like the formal way to do that would be like to write down the second order Taylor expansion or something. You see that this is basically a linear sum of the last 3 states. So you can do this sort of curvature estimation in a very coarse sense, at least, by attending locally.
Right.
But I think this like becomes much
an
more
intuitive way of
putting
putting that, but I'm not sure if this is correct. Would be to like on this last one, if we look at the last 3 points, for example, as you look at the difference between the differences of the last 2 versus the second last one and the third last one.
Yeah.
So you look at those 2 vectors and you look at the difference between those, and then you add that to the difference of the last vector. And then you can imagine getting a curved vector that goes one onwards.
Yeah, it's something like this, I think. Yeah.
And that, I think that's just exactly the Taylor expansion that you're discussing. Okay, so yeah, so I'd be curious to like see if you can go like deeper into the interpretation of even in this toy task of the weights, and be like, is that operation like you've got a clue that this is what's happening with the attention score, but it could be that like you can actually read off the weight matrix and see that, hey, look, this Taylor approximation is exact.
Oh yeah, that would be super neat. I agree. Yeah, it's a great suggestion.
But yeah, this is cool. Dushan, can you figure out how to get Matthew to be able to answer? I'm not sure.
Yeah, got it.
Hello, can you hear me?
Hi, yeah.
Yeah. So with the non sequitur effect, where you were seeing sort of deviation, like the way I'm understanding it, which might be completely wrong, is that this is kind of like, there's the in weight learning sort of manifold that then is being sort of pulled to the forefront by your task and kind of refined in context learning. And then when you hit this non sequitur, you've kind of got the prediction from that combination of in context and in weight learning going wrong and like not being what the model actually sees. And it just strikes me that this is, if I'm understanding it correctly, kind of like a very root level moment in the model's sort of the model's model of the world diverging from the real world, and kind of you can be relatively confident in a way that other things have to be downstream of this particular effect, like sort of confidence and surprise, and sort of like you can't be confident in whether your model is correct, or like you can't lose confidence in your model until your model has diverged. You can't be surprised until your model has diverged. And it seems to me not only does that have a nice link to things like sort of confidence and things that are very important from a safety perspective, but thinking back to Yoon's talk yesterday on consciousness, that this is sort of, and it like you could sort of define changes in model behavior downstream of this detection of a non sequitur as perception of there having been a non sequitur. Distinct from this moment that you're seeing here, which I think is kind of earlier than that. And I just wondered, sort of what are your plans downstream of having this sort of detection method?
Yeah, so first thing to say is I most certainly share this intuition, and that's what I try to look for. I'm not at all confident that it's actually what is going on. But it seems like the model in some sense is going off the beaten path or beaten manifold, right? Like the kind of, it's kind of like out of, it has to go to some out of distribution manifold. That makes sense. Yeah, where to take this? I don't know. I think there are like many possibilities. I think it's an intriguing idea to look for neural signatures of consciousness, for example, as Ewan was saying yesterday. Like this would be more the Mac-interp side of things that he alluded to. Yeah, I think there's also like, I think this again alludes to this more general paradigm that Jan and I were outlining, like looking at somehow like sets of states as opposed to single states, just like opens up a whole new like so many possible things to research for, which people are already getting started on. So I think there's lots to do.
Yeah, no, I think it looks super cool. I just want to say, I think it's really interesting that kind of the neuroscience representations were so far ahead of kind of the machine learning ideas until like now with the manifolds, it's like 2022 and 2024, like we're converging. Anyway, super cool work. Thank you very much.
Yeah, last opportunity for questions. Okay, nice. Dushan, do you mind just organizing the saying all the things for the breakout room? And
thank you, Jan. We'll stop the recording here. Thank you for the talk.
Most welcome.